Yeah.
You moved the quiz to Monday?
Yeah, Monday.
Oh. There was. Yeah. I don't know, that's good. That's not.
This course, please refer to the last Eagle update and Milton Eagle social media.
Don't phrase it.
And I like it. I've been playing. It's like 20%. Like important. Talking about this.
This is what we covered.
Okay, the top.
Okay, calendar here. So, today we're going to start basically we're starting the second semester topic for AP Calculus. So we're moving into antiderivatives, kind of moving towards undoing the process that we learned with derivatives. And the first semester was all about slope. Sorry, first semester AP Calculus is all about slope. Second semester AP Calculus is all about area under the curve, because they are going to be very much inverse processes of each other. So we'll do that today. Tomorrow we'll do we'll continue with area using rectangles and trapezoids to approximate area under the curve. And then along the way, we can try to squeeze in some practice problems. So you guys picked up a quiz review packet. I already gave you a review packet, but this is just packet that I copied from my AB class. So this is not going to be required anyway. This is just for additional practice if you would like to do additional practice. And also I'll pick out problems from this packet for my help sessions tomorrow morning and Monday morning. Okay. But this first page though is useful in helping you narrow down your focus in terms of what you're going to be studying for on Monday's quiz. So there's going to be extreme value theorem problem where we have to find max and mins on the closed interval. Be sure to state our condition. Remember, there's one condition, right? That's continuity on the closed interval. Mean value theorem is where we're trying to find the slope, guarantee a slope between the two endpoints, right? So we find the slope between the two endpoints. We set it equal to the derivative. And we're asking the derivative to find where else on the curve is there a slope that matches between the two endpoints. There are two conditions with mean value theorem, right? Continuity on the closed interval and differentiable on the open. Rolle's theorem is basically the same thing as mean value theorem. It's just that Rolle's theorem, we're looking for a slope of what? 0. Yeah, slope of 0. So that means my endpoints do have to share the same y value in order for that to happen. So Rolle's theorem is kind of like it's like one specific case under a larger mean value theorem umbrella. First derivative test. This is where you find f prime. You create your f prime sign line, and then you use justifications, your because statements, to indicate where the graph is increasing, where the graph is decreasing, where there's a relative max, where there's a relative min. So I think most students feel this is pretty straightforward, right? No issues here. Test for concavity, we do the same process, but on the second derivative line. But information that you're gathering, even though this you're going through the same process, the second derivative is giving you a different set of information, right? Your critical points are no longer relative max, relative min. Your critical points are now points of inflection. And then your intervals are no longer increase, decrease. They're concave up and concave down. There's also second derivative tests, which sounds like what test for concavity should be, but the name second derivative test is a test for relative max and relative min. It does the same job as the first derivative test, but rather than taking the critical points and plugging them onto your sign line, you're taking your f prime critical points and inserting into your second derivative function to gather if that point is part of a concave up or concave down. And from that, you can decide whether it's a relative max or relative min. Okay. We don't do points of inflection for second derivative test. That's test for concavity. Interpreting derivative graphs. This is the one that we did together in class, where you had to create an f prime sign line, f double prime sign line. You got to use what they give you to create your f of x graph and your f double prime graph. So we'll see an extended problem like this on your quiz. And I also included a couple of these in your packet as well. And then there's going to be one optimization problem. It'll involve cost, but it'll either be cost involving area perimeter, or it'll be cost involving volume surface area. And I included a couple of those in your packet as well. So this is what your quiz will look like. You will get to use your calculators. Quiz is Monday. Any questions? All right. All right, let's move into our Unit 6 packet. Okay, so area under the curve. The region between the function and the x-axis is called the area under the curve. Under, in this instance, doesn't mean below. It just means between the x-axis and the curve. So sometimes it's not very clear where the x-axis is. So we go ahead and shade those in. Whenever we're talking about area under the curve, yeah, it just means between the x-axis and the curve. So let's take a rate of change function and examine its graph. The area under the curve gives us the accumulation of change. We're adding up this quote unquote change over a period of time. So here's an example. You're on a road trip and you have your car on cruise control for 4 hours. You travel at 60 miles per hour for an hour. You travel 60 miles per hour for 4 hours. How far have you traveled? So if this is our velocity graph, we're holding steady at 60. But if we want to figure out how far we travel, we're accumulating that rate of change over a 4-hour period. So if we accumulate change, then we're basically using area to represent how far we've gone on that trip. So if we travel 60 miles per hour over a 4-hour period, we're basically doing 60 times 4, right? Basically, that's going to be a rectangle. So that tells us that, okay, we're able to move from velocity information up to position information if we just involve area. Right? We're able to find slope information or rate of change information if we found slope, but if we found area, we're able to go the other direction. So the reason why slope and area kind of have this inverse relationship is if you think about slope, right? Slope is change in y over the change in x. Right? The main process here is division, right? We're dividing change in y over change in x. If we start off with meter, then we end up, then our derivative will be meter per second. So the main process here is division. What if we were to undo division? What process will undo division? Multiplication, right? So if I were to multiply these together, look what happens. What is this giving us? So if I have x sub 2 minus x sub 1 times y sub 2 minus y sub 1, we're getting a what? Area, right? So that's why when we're doing antiderivative, when we're undoing our derivative process, we're going to be dealing with a lot with area because area is going to undo my process for division. So, so a lot of what we talk about is going to be area related. Okay. So units for area under the curve, it's not the same as starting units. The dependent unit multiplied by the dependent unit is multiplied by the independent unit. In other words, unit for y times the unit for x. All right, so if we're accumulating velocity over a 4-hour period of time, our units is going to change, right? Miles per hour is going to turn into miles, because I'm multiplying this unit by this unit. Right? So 60 miles per hour times 4 hours will give me miles. So just like how if we found the derivative or slope, we're always changing our rate, right? We're dividing by something. But now if we're undoing that process, we're going to be multiplying that by something and our units will undo itself. So here, the graph represents the rate at which water is leaking out of a tank. The units are given in the graph. How much water has leaked out of the tank after 9 minutes? So let me start off with this one. So we know that if our graph represents gallons per minute, if I find the area between the graph and the curve, we're basically having to multiply these two units together, right? So gallons per minute times minute, if we accumulate this over a period of time, we're going to be able to figure out exactly how much water has leaked out. So gallons per minute times minute, we're always multiplying, because we're involving area, we're always multiplying our units. And so our starting units will always change if we're involving area. So here we have a couple of geometric shapes here. You got a rectangle, you got a semicircle, you got a triangle. So if we add all that up, because we're accumulating this rate over a period of time, if we use multiplication, if we use area, we can find out exactly how much water has leaked out given our rate. So rectangle is just width times height. Semicircle is just 1/2 pi r squared. Triangle is just 1/2 base times height. Add all that together. Our units of measure was gallons per minute. But now over this 8-minute period, we're able to accumulate that rate over that 8-minute period. So what we gathered is now the area represents the amount that has leaked out, 15 plus 2 pi gallons. And we can also apply this to particle motion. Particles moving along the x-axis. And the rate is modeled by RFP. RFP basically represents your velocity. So we're looking at a velocity graph here. So let me just follow this graph and just kind of talk about what information we can gather about this particle as it moves. So this tells us that it starts off moving at 10 centimeters per second, positive. So we're moving to the right. It's going to keep moving right until all of a sudden, at 2 seconds, it's going to stop. Then it's going to do what? Change direction, right? So it starts going to the left. And it's going to start going left. It's going to pick up speed. It's going to hold its speed. It's going to slow down, but keep moving left. And it's going to stop, start moving to the right, and then start picking up speed in the other direction. And if we involve the area under between the graph and the x-axis, we can figure out exactly how far this particle has traveled in its respective direction. So here, above the x-axis, we know that this will be positive. Yeah, this will be how much ground he's covered in the positive direction. And if we find the area here, this will tell us how far he's traveled in a negative direction. And then this will tell us how far he's traveled back in the positive direction. Okay, so part A, how far is a particle from its starting position after 10 seconds? So we can figure out how much he's traveled to the right, how much he's traveled to the left, how much he travels to the right. We add those numbers together and we can figure out where his displacement is going to be. And then our units will be different as well, right? If we're starting with centimeters per second, but if we're revolving area, we have to multiply these together. Centimeters per second times seconds, we're going to end up information giving us in terms of seconds. So I'm just using geometric shapes to find my area. You may be breaking it up in a different way. You may, I mean, if you want to, you could use trapezoids if you wanted to, but I think we just prefer triangles and rectangles. So positive 10, this triangle is negative 22.5, negative 30, negative 7.5, and then back to positive 10. So first he's going to go 10 units to the right, then he's going to go mostly to the left, cover a lot of ground, and then he's going to go back to the right 10. And so what's going to happen is over this 10-second period, he's going to end up, that negative 40 indicates he's going to end up 40 centimeters to the left of where he started. Okay, all the other examples are just using that same concept. Let me go into 6.2 because 6.2 is a little bit longer and we may need to pick up on 6.2 tomorrow, but there's not much with 6.1. Okay, so page 7. So if we have a curve, we're going to be spending time trying to, eventually we're going to find the exact area under the curve. But right now we're going to use geometric formulas to find areas of these curves. And the easiest shape that we know is rectangles and squares. So we're going to just basically use rectangles to approximate an area of a region. And that's what Riemann sums is. We're just using rectangles to approximate region. Obviously, we can increase our accuracy by having smaller intervals and smaller rectangles to cover all the potential gaps. But we don't have to worry about how accurate our approximation is. We just have to provide the approximation and the number of rectangles that the problem is asking you to do, and the type of rectangles that you're going to draw. So let's read this here. The graph of the function g of x is shown. Approximate the area under the curve, in other words, between the curve and the x-axis, on the interval from 2 to 6 with n subintervals by using a left rectangular approximation method. So let's say we start off with n equals 4. We're going to start off with 4 subintervals here. So the formula, especially if we want to build subintervals that are equal width, our width formula to ensure we get equal width is going to be b minus a divided by n. So we figure out the endpoints and we subdivide it equally amongst however subintervals we want to have. So in this case, our width is just going to be 1 because 6 minus 2 over 4 is just 4 over 4, which is 1. So this approximation method is called Riemann sums. Named after a mathematician. So we want to do a left approximation method. So what we want to do is we're going to be creating 4 rectangles. One rectangle is going to be here, second rectangle, third rectangle, fourth rectangle. 1, 2, 3, 4. Let me zoom in so you guys can see a little bit better. Now, the reason why some of these rectangles may be different is because we're going to be attaching either the upper left corner or the upper right corner to the graph, okay? Because we want the graph to tell us the height of these rectangles. This is a left rectangle, so that means for each subinterval, we want to choose a left subinterval to attach to the graph. So here, it's going to be at 2. So go ahead and highlights that order pair at 2, where your vertical bar is going to meet the curve, and that will be the height. So you're going to drag that height across so that you can see the shape of a rectangle begin to show up. So this is considered a left rectangle because we're purposely attaching the upper left corner of each subinterval to the curve. For the second rectangle, 3 is the left endpoint. So we're going to, from 3, we're going to find that y value, highlight that, drag that height over. That's going to be the height and the shape of your second rectangle. Third rectangle is going to be at 4. Highlight that point, drag that height over. The same thing at 5. Highlight that point, drag that height over. So if I want to find, obviously this is not going to be the exact area under the curve. We see all these gaps here, but it's an approximation. So we just do width times height, and just add them all up. All right, so let's start doing that, starting with this one here. So we'll start off with 4x minus 1/2 x squared. You have 4 different graphs, 4 of the same graphs, but each of them will be asking for you to draw rectangles a little differently. So we have left Riemann sum, right Riemann sum. midpoint Riemann sum, what that means is we're going to attach the midpoint of each subinterval to the curve and let that midpoint attachment to the curve represent the height of that subinterval. And then finally, trapezoids. Okay, so first we want to find the width. So width is b minus a over n. So the width of each subinterval is going to be 2. So we're starting at 2, and we're going all the way to 8. So 2 to 4, 4 to 6, and 6 to 8. So these will be my subintervals for my 3 rectangles. Okay, so let's practice that. See if you can attach appropriately to the curve, depending on whether it's left, right, or middle. And then find the width and the height of each subinterval, add them up, and that's going to be the area of your 3 rectangles. And try a right Riemann sum. So now within each subinterval, you're going to purposely pick the right endpoint and let the right endpoint represent the height for that entire subinterval. Any questions, Celeste or right Riemann sums? So now the midpoint is where you're going to find the midpoint within each subinterval. So that means for us, it's going to be 3, 5, and 7, right? So find out where the graph is going to be at 3, at 5, and 7, and let that represent the height of each of your subintervals. You may have to do a little bit of approximation because some of these y values may not be very clear, but I'll just pick like 7.5 or just a number that is convenient. assuming we have the same number of intervals, which do you think would be the most accurate between left, right, or midpoint?
Midpoint.
Midpoint is going to kind of minimize that the amount of gaps. It's not perfect, but it's better than left and right, assuming we're using the same number of intervals. Are we good with the first three? Now, the best approximation is not going to be a rectangle shape. It's going to be trapezoids, just because the way that trapezoid is able to kind of mold to the shape of the graph the best. Now, you may be more familiar with a trapezoid that is drawn this way, where you have two parallel bases and the height, and the formula is 1/2 height, base 1 plus base 2. But the way that we're going to draw the trapezoid, we're going to flip it on its side. And so because of that, I'm going to have the vertical be H1, H2, height 1, height 2. And then my horizontal be the base. So I'm just going to slightly adjust the formula. I'm going to refer to the formula for trapezoid this way: 1/2 base or 1/2 width, if you want to use width. Okay. So we're going to draw our trapezoid in a slightly different orientation. And what we're going to do is, if our interval is from 2 to 8, we're going to attach every height in our subinterval. So we're going to attach, highlight the point at 2, highlight the point at 4, highlight the point at 6, highlight the point at 8. And you're just going to connect from peak to peak with all those dotted lines. Now, if you look, this third shape is not really a trapezoid, right? What is it?
Triangle.
It's a triangle. But we can still use a trapezoid area formula, because if one of the heights zeroes out, then it turns into a what? It turns into what formula?
1/2.
1/2 width times height, right? So we don't have to worry about, oh wait, that's a triangle, I need a different formula. We use the same formula for triangles, because one of the heights will be 0 and it'll turn into a 1/2 width times height. It'll turn itself into a triangle. But if you look at the way that trapezoids are shaped, even with just 2 trapezoids and I guess 1 triangle, there's already a very minimal gap, right? It doesn't jut out like rectangles do. So one takeaway from this is sometimes AP exams would ask you, okay, can you order the accuracy of the approximations, and trapezoid will be the best, midpoint will be second, and then the left and right will be last.
The left and right of equal accuracy.
Depends on the shape of the graph, but you're not going to be asked to determine the accuracy between left and right. Yeah, sometimes the shape of the graph causes left to be better or right to be better, but
So will it just be like determine the accurate order of the accuracy between trapezoid and midpoint?
yeah, trapezoid followed by midpoint, and then left and right is last.
Oh, they only would people.
Yeah. So you will never have to worry about, okay, is left better or right better? We don't, yeah, we don't have to worry about that. So our formula is 1/2 width times height 1 plus height 2. So here, my width is always 2. So 1/2 2 times f of 2 plus f of 4. That's the area of one trapezoid. Second trapezoid, 1/2 width, f of 4 plus f of 6. And then last one, 1/2 width, f of 6 plus f of 8. And if we add all that up, that's going to give us an area of 34. Which will be the best, most accurate amongst these three, amongst these 4 approximations. Yeah.
Why did mathematicians come up with the ones before trapezoid?
Why what?
Why did they even come up with like 3 months right so?
Yeah, so eventually what we're going to see is that we can improve the approximations, because, well, the ultimate goal is we want to find the exact area under the curve, right?
Yeah.
So what if we were to increase the number of rectangles? What is that going to do to our accuracy?
It's gonna increase.
Right, it's gonna improve it, right? So that kind of begs the question, well, what if we have infinite number of rectangles? And then technically that should lead us to the exact area. So again, we're going to invite limits into our process to find, add up infinite numbers of rectangles, use limits process to find the area. And we always have this lengthy process of learning the process first, and then we're going to go through a much faster route with power rule, just like how we did with derivatives.
So then what would the approximation be used for if later on we're going to learn how to find the exact?
Yeah, good question. Yeah, we're going to see on the next page where approximation is an important process. And sometimes on the AP exam, they will say they don't even care about the exact value. They'll just say, use left Riemann sum to approximate this value. So we have to know how to use rectangles and trapezoids for approximation. And then there's also other parts where you're asked to find the exact value, and then we can involve calculus. Yeah, just like with derivatives, right? Sometimes you may be asked to find instantaneous rate of change. Other times they may just ask you for the average rate of change, and the average rate of change is just approximation. So they're always playing between approximation and exact, and we do need to know how to do both. So typically, this is not the way that AP exam will ask you questions about approximating an area of a rectangle, area of a region. Typically, they will give it to you in the table of values. So I want to show you what that looks like on the AP exam. So page 8. So this is very common, very popular on the AP exam. You're almost guaranteed that you're going to see a problem where it says you're going to be given a table of values, and they're going to be asking to approximate a certain value using rectangles and just given these values. So the rate at which water is being pumped into a tank is given by the continuous and increasing function R of t. A table of selected values of R of t between 0 and 12 minutes is given below. So that means, let me just kind of talk through what these numbers are telling us. So at 0 minutes, water is being pumped in at a rate of 7 gallons per minute. Okay. 3 minutes, that rate is going to increase. So the faucet is letting out more water, 13 gallons per minute. And it's going to keep increasing, 18 gallons per minute, 23 gallons per minute, 27 gallons per minute. So the volume that water is coming in is going to come in at a higher and higher rate as time passes. So it says use the following Riemann sums to estimate the number of gallons of water pumped into the tank during the 12-minute period. So the idea is that, well, if I have all these rates and I have how much time passes, I can approximate how much water has entered into the tank. So essentially, we're multiplying these two units together, right? Gallons per minute times minute. And if we want to multiply those together, we're going to use area and we're going to use rectangles. Okay, so it says write Riemann sum with 4 subintervals. Okay, so the way that you're going to draw these 4 subintervals, you're going to have to figure out how can I draw 4 equal subintervals. Not all the widths will be the same, like how we see here. Okay, so the way that you're going to draw these subintervals, make sure that you start at the middle of your order pair and not at the corner. If you start at the corner, it's going to mess you up. So we're going to 4 subintervals. So we'll do from 0 to 3, 3 to 6, 6 to 9, and 9 to 12. Right? Those are our 4 subintervals. So you're going to do this. You're going to start at the middle of your order pair and then go to the middle of your next order pair. That's one subinterval. Next subinterval, pick up where you left off. Don't go to 6. Start at 3, 3 to 6. Okay. And then 6 to 9. And then 9 to 12. So those are your 4 subintervals. If you start drawing your rectangles at the edges, it's going to be tough for you to see. Yeah, it's going to make it more difficult. So just every time you draw subintervals, start from middle to middle. Okay, middle to middle. Now, what is the width of my first subinterval? 3. I'm just subtracting, right? Second subinterval is also 3. Now, with AP exams, typically the widths are not going to be the same, but just want to let you know that. Sometimes they're the same, but a lot of times they're not. We want to write Riemann sums, so we want to find the width and the area, sorry, the width and the height associated with our area here. So the width of my first rectangle is 3. What is the height of my first rectangle? If I want to do write Riemann sums. 7 or 13? 13. So 13 represents the height. I want the height of my right endpoint. So 3 times 13. My width and height for my first rectangle is 3 times 13. Does that make sense? Okay. Second rectangle, 3 times what? 3 times 18. Next rectangle, 3 times 23. Plus 3 times 7. Okay. How is my units going to be affected? It's now going to be what?
Yeah.
Good, gallons. Whenever you go through Riemann sums, your units will always change, okay? We're not going to be talking about gallons per minute anymore. We're talking about gallons because we're multiplying these together. Yeah. Question? Okay, try left Riemann sums. Yes. Huh? Do you round it? What do you mean?
The number of gallons.
We know this is an approximation. Is that what you're asking? Yes, yeah. So we say a squiggly line because obviously we don't know the exact, but we're just doing an approximation. Okay, let's do left Riemann sums. Oh, by the way, I just got an email from admin that they're going to be adding a bell that's going to signal the end of second period and the beginning of advisement. So you'll hear a bell at 10:12, I think. All right, try left Riemann sums. Is that what you guys got? 183. Okay. So now the next question is the approximation greater or less than the true value? Now, this is what we know about our shape of the graph, right? We know that our graph is continuous and it's increasing. So this R of t is always growing. So if I draw what's happening here, if I'm attaching the right endpoint to every one of my curve, what do you see about these rectangles here? They're all going to be slightly above. There's always a portion that's sticking above. So I know that because I have an increasing graph, my right Riemann sums will always be an over approximation. Now, these are things that I don't want you guys to memorize. I just want you to be able to draw it, right? If you can draw it, you should be able to convince yourself, okay, is my rectangle sitting above or below the curve? If my rectangle is above, then it's going to be over approximation. So I don't want you to feel like you got to memorize, oh, wait, okay, increasing left, okay, that must mean under approximating. Or better yet, if you can visualize drawing it, but I don't want you to feel like you have to memorize these steps. Next up, is approximation greater or less for left Riemann sums? Well, because my graph is rising and I'm letting the left endpoint represent the height of each subinterval, I can convince myself that all these rectangles are going to be inscribed. And so it's going to be less because there's gaps above the rectangle below the curve. Okay. Any questions? Okay. Everybody good? Let me talk about midpoint. Midpoint, you're not necessarily, I think sometimes that word is a little misrepresented. It's more like middle or in between. It doesn't have to land exactly in between. It just has to be a number that's so this is what I mean here. It says middle rectangle with two subintervals. So if it's a middle rectangle, they always have to give you 3 ordered pairs so you can physically pick out the middle one. You're never going to have to find the average of 2 numbers. There's always going to be a middle order pair for you to pick out. So in this case, I have 7 to 18, that's one subinterval, and then 18 to 27, sorry, 0 to 6 is one subinterval, and then 6 to 12 is the second subinterval. Okay. Each subinterval, in this case, is a width of 6. And we can physically see a middle ordered pair. It may not always be between 0 and 6. It could be at 1, it could be at 5, it could be at 3.6. But you're always going to be able to have a physical Y value to pick out from. You're never going to do any additional, average calculations. So my first rectangle is going to be a width of 6 and a height of what? Yep, it should always show up. Okay, so you're never going to be doing middle rectangle with an even subinterval. There's always going to be an odd subinterval where you can pick out the physical middle Y value to choose. So first rectangle is 6 times 13. Next rectangle is 6 times what? 23. Yeah. Finally, trapezoid is 1/2 width, height 1 plus height 2. Okay, so we have 4 subintervals. We have to do 4 separate calculations. So first trapezoid is 1/2 of 3 because that's the width, and then height 1 plus height 2, 7 plus 13. Oh, I do want to talk about a trouble spot with trapezoids. So this is what I've seen some students do. Let me go back to this diagram here. What if it was 2 trapezoids? So this, right? So first trapezoid will be 1/2 times 6. And it's going to be what? What heights do we want to use?
7 and 18.
Good, 7 and 18. Then 1/2 times 6 and 18 plus 27. Okay. The reason why this is a trouble spot is because I see some students feel like, oh, I got to add up all the heights. But remember, your trapezoid formula only has 2 heights associated with it. So we don't want to say 1/2 6, 7 plus 13 plus 18. Then we're changing the formula. That's not the area formula. There's always only going to be 2 heights associated with the trapezoid, and you're only going to be using the ones where your bracket is ending. That makes sense. So we don't want to do this. Okay, good. So we got through the first part of 6.2, but your homework will just be from 6.1. So follow your calendar. Sorry, I didn't get a chance to do quiz review, but I will be available tomorrow morning help session. All right, go get your phones.
Good.
So,